I'm going to try and give you an overview of indoor ozone and ozone-derived products as it relates to Far-UV. I think you all appreciate that ozone, increases in outdoor ozone lead to increases in adverse health effects. And there are numerous studies by epidemiologists from around the world looking at... Thank you.
Can you hear okay?
Better?
Yes.
My apologies. Numerous studies looking at the adverse health effects of ozone, both short-term and long-term. There's two very large studies actually looking at the long-term health effects of exposure to ozone. A 10 pp increase in long-term ozone exposure has been associated with a 12% increase in respiratory mortality, a 3% increase in circulatory mortality, a 2% increase in all-cause mortality. Now, when the epidemiologists do these studies, they typically measure ozone at a central outdoor site where they model outdoor ozone concentrations over a large geographic area. But the individuals whose health they're monitoring, those individuals are both outdoors and indoors, and the epidemiologists do not quite distinguish about when they're outdoors and when they're indoors. So they're actually capturing three different exposures, if you will. There's inhalation of outdoor ozone when the people are outdoors. There's inhalation of indoor ozone when the people are indoors. And there's inhalation of products derived from ozone-initiated chemistry that's occurring when they're indoors. Now you notice on this slide, I don't have inhalation of ozone-derived products when they're outdoors. That's because the concentrations of the products outdoors are much lower than the concentrations indoors. So to a first approximation, we can ignore inhalation of ozone-derived products outdoors. You all appreciate that Far-UV generates ozone. The ozone generation rate, we'll call it G in this presentation, is proportional to the actinic flux. Ozone can also be generated by a corona discharge if it occurs with the operation of the lamps. The resulting ozone participates in indoor chemistry, both surface chemistry and gas-based chemistry. In typical indoor environments, the chemistry is dominated, the ozone reactions removal process is dominated by surface chemistry, but gas-based chemistry is also important. A good example of surface chemistry is ozone reacting with compounds in our skin that contain carbon-carbon double bonds. And it can be either on our exposed skin or on surfaces that we've soiled by our touch or by our skin flakes. Gas-based chemistry, a good example is ozone reacting with limonene, which is a common scent agent. It could be that fruit scent or an orange scent, depending on whether they're using a mix of isomers or just one isomer. Now, if there are no indoor sources of ozone, we have a good idea of what we can expect in terms of the indoor ozone concentrations. Many studies have measured ozone in homes, in schools, and to a lesser extent in offices. And typical indoor ozone concentration, central tendency, about 5 ppb. You can see an interquartile range for homes and schools. That's on the order of 2 to 10 ppb. Now these indoor concentrations, this is in the absence of an indoor source of ozone. This is when the only source of ozone is outdoor, indoor transport. Well, the indoor concentrations under those situations, when there's no indoor sources, is substantially less than the outdoor concentration. and that's because of these reactions, ozone reacting with surfaces and ozone reacting with species in the air. That's consuming the ozone. So the ozone that's measured indoors is a residual concentration. It's what's left over after ozone has reacted with ozone-reacted species on surfaces and in the air. Under steady-state conditions, you can estimate indoor ozone concentration from outdoor ozone concentration reasonably well with the simple expression shown in the box here. And this expression, thank you. Is that better? Yeah. In this expression, we have a term in the denominator. That's the rate at which ozone is coming into the indoor space. It's simply the air change rate times the outdoor ozone concentration. And we have in the denominator the sinks, which is the ventilation rate, and a first order rate constant that describes the net removal of ozone by chemistry. So this expression does a reasonably good job of allowing you to estimate indoor ozone concentrations if there's no indoor sources. Now, in this schematic, you see outdoor ozone entering the indoor environment. You see it reacting on surfaces. You see it reacting on the surfaces of the occupants. And that's important, reactions on the surfaces of occupants. And reacting with compounds in the air. And in each case, you generate products. And the occupants can inhale those products or ingest those products if they attach themselves to dust, or in some cases, if the product has the right chemical properties, they can be thermally absorbed. We are interested in these products. It's very difficult to speciate these products. It's expensive. If you want to simply get an estimate of the net concentration of products, you can look at the difference between the outdoor ozone concentration and the indoor ozone concentration. We'll call that ozone loss. And the ratio of ozone loss to ozone itself can be estimated by a very simple expression, K over lambda. And I remind you that K is that first order rate constant for surface removal, and lambda is the air change rate. Often K is larger than lambda, so this is telling us that often ozone loss is larger than ozone itself. The net concentration of ozone-derived products is proportional to ozone loss. That's where ozone loss is really useful. Now, some people are under the impression that a lot of ozone disappears, if you will, when it reacts indoors, that it's catalytically destroyed. In most environments, that's not the case. You can design surfaces in such a way that only a small number of products will be generated by the reactions. But in most environments, that's not the case. In most environments, the chemistry is resulting in products. Now let's turn our attention to ozone generated by Far-UV. The incremental addition of ozone, when you use Far-UV, can be estimated by G divided by K plus lambda. It makes sense. It's basically the rate at which you're emitting ozone to the room, G, divided by our two sinks again, K and lambda. We can also calculate something equivalent to ozone loss for the ozone that's been generated by the use of Far-UV. In this case, I'll call it ozone loss UVC. It's the amount of ozone produced by Far-UVC that's subsequently consumed by indoor chemistry. Once again, we can estimate the ratio of these ozone loss to ozone from Far-UVC, it's the ratio of K over lambda. A little bit of the algebra will show you that that's really the case. And the net concentration of products, ozone-derived products, resulting from turning on those lamps, that can be estimated by ozone loss. Not all organic compounds in the air or on the surface react rapidly with ozone. Ozone likes compounds that have carbon-carbon double bonds. Examples, limonene. You see limonene, this scenting agent, it has a double bond in the ring and an external double bond. Squalene. About 10% of our skin oil is squalene. It's a magic molecule. I really like it. And it gobbles up ozone. But you also get a slew of products. Oleic acid. That's common in cooking oils. If you use an unsaturated oil, it likely contains oleic acid. Olive oil, high concentration of oleic acid. But I also have on this slide common indoor pollutants that react with ozone too slowly for the chemistry to be meaningful indoors. N-hexane, cyclohexane, hexanol, a large list. Roughly 10% of the organics we encounter indoors are ozone-reactive compounds. What happens when ozone reacts with that double bond? It actually adds across the double bond. And on this slide, you see what's called the primary ozonide. That primary ozonide, it's unstable. It just has too much energy. Something has to happen. You see the primary ozonide decaying on this slide to two products. Call it product 1 and product 2. Product 1 is typically an aldehyde or ketone. Product 2 is what we call a dicarbonyl. And it can break in two different ways. I'll just flash back and forth so you can see how that primary ozonide decays. And now that influences the R groups on the aldehyde and the Kriege intermediate. An important point I want to make on this slide is that if the double bond is not in a ring, you're getting two products from whatever the original molecule was that reacted with ozone. So your yield of products is roughly twice the concentration of the species that react with ozone. Now, another point, that Kriege intermediate, product 2, that Kriege intermediate decays by multiple pathways. One of those pathways takes you to the hydroxyl radical. And the hydroxyl radical is important because it reacts with everything. I told you ozone likes those compounds with carbon-carbon double bonds. The hydroxyl radical will abstract the hydrogen from almost all organics. It also likes double bonds. So the hydroxyl radical is capable of oxidizing those compounds that don't react with ozone. The fact that ozone itself is a source of indoor hydroxyl radical broadens the amount of chemistry that's occurring indoors. So together, these two oxidants, ozone and hydroxyl radical, generate products with a range of volatilities. You have highly volatile products that exist primarily in the gas phase. That's species like formaldehyde, hydrogen peroxide, acetaldehyde. You have what we call semi-volatile organic compounds. These are compounds that partition between the gas phase and indoor surfaces, including the surfaces of particles or dust. And then you have and examples there are nonenal or succinic acid, or peroxyacetyl nitrate, PAN. You have relatively non-volatile products. They basically stay on the surface where the chemistry has occurred. I'll remind you, when we're talking about ozone-derived products from the use of UVC, we can estimate the concentration, the net concentration of these products by using this ozone loss, UVC term, which is estimated as the amount of ozone produced by Far-UVC that's subsequently consumed by the chemistry. And you see again the expression for that. Now, what are some of the products of concern? Well, we have both stable products and short-lived, highly reactive products. I won't read the whole list, but I've highlighted some of the products that give me the greatest concern. Dicarbonyls, organic peroxides, diol epoxides, organic nitrates, secondary organic aerosols, and I'll say a little bit more about the secondary organic aerosols. Short-lived, highly reactive species, hydroperoxy radicals, alkyl peroxy radicals. Then we have compounds that are thermally stable but react rapidly with water. So if you were to inhale them and they encounter moisture in our respiratory tract, they quickly decompose to reactive oxygen species. And two examples there are secondary ozonides and organic hydroperoxides. So these are some of the products of concern. Fortunately, their concentrations are normally quite low. So, a little bit more on secondary organic aerosols. The products that have low volatility, those products can either condense on existing aerosol or they can nucleate to form new particles, new aerosols. We can use ozone loss, or UVC, to estimate the secondary organic aerosols that are formed in an indoor environment when you use the Far-UV. To do that, we'll define a yield term, yield SOA, and that's going to be defined as the mass concentration of SOA produced per mole of ozone loss. So, for example, micrograms per cubic meter of SOA per mole of ozone consumed. The literature suggests that yield SOA is in the range of 0.03 to 0.07. It's relatively small. Only about 3 to 7% of this ozone loss is resulting in secondary organic aerosols. But it's of concern because the epidemiology tells us that the secondary organic aerosols have much larger potency than ozone itself. Paula showed this in her presentation that kicked things off on Tuesday. Wednesday. Okay. I want to make another point, just how important the occupants are as sinks indoors. I'll give you two examples here, and the examples actually highlight several aspects of this chemistry. The first is using a hotel room that was so nicely described by Petri Kawiyamaki yesterday. And I've used parameters that are appropriate for what was measured in that hotel room. The air exchange rate I've used is 1.4 air changes an hour. The net rate constant for ozone removal I've used is 2.9 reciprocal hours. Well, if the hotel room is empty, which it was in those experiments, then we can use those equations I showed you earlier to estimate the ozone resulting from UVC at about 5.8 ppb. And for the products, and this is the combination of gas phase and condensed phase products, for the products we estimate a concentration of net products of about 24 ppb. So in this case, you see the net concentration of the products is substantially larger than the net concentration of ozone itself, speaking about what's resulting from the use of the UVC. Now, we have two occupants in that hotel room. The first order rate constant increases. First order rate constant for ozone removal increases from 2.9 to 3.9. The steady state oxygen concentration goes down from 5.8 to 4.7. The net concentration of the products goes up from 24 to 26. So the occupants make a difference here, but it's not a huge difference, right? Now consider a classroom. We consider a classroom when it's empty and when it is occupied by 35 students. And I'm using the classroom that's defined in the ASHRAE ventilation standard, 62.1. I won't go through all the parameters. We'll just jump to the ozone concentration resulting from UVC in the classroom when it's empty. And that's 4.2 ppb using the equation we saw earlier. And the concentration of products is roughly twice that, 8.2 ppb. Notice now that the concentration of products relative to the ozone itself is substantially lower. Well, that reflects the fact that in this example, the air change rate is 3 air changes an hour rather than 1.4 air changes an hour. With 35 students in the classroom, that rate constant for net removal by indoor chemistry, that rate constant goes from 2.9 reciprocal hours to 6.4 reciprocal hours. The ozone has been reduced. These bodies are sinks for ozone. It goes from 4.2 to 2.7 ppb. The net concentrations of the products go from 8.2 to 11.4. It's just to give you a feel of how occupancy affects the environment. And you really want to pay attention to occupancy when you think about the chemistry that's occurring. Mitigation. We really can take steps to reduce the occurrence of this chemistry. You can operate the lamps at an actinic flux, as slow as necessary to kill the pathogen. You can avoid radiated emission at wavelengths less than 200 nanometers. You're the experts on these first two bullets. You can minimize the use of ozone-reactive chemicals in environments where you're using Far-UV. I don't think it's unreasonable to ask to try and limit the use of scented products in an environment where you're using Far-UVC. Cleaning products, you pay attention to cleaning products as well, and the constituents of those cleaning products. And there's certain chemicals that you could deliberately try to avoid. I don't think that's unreasonable. I think you all appreciate how useful it can be to increase the ventilation rate. Those equations drive that home. You can also remove the ozone after it's been generated. If you're in an environment with a mechanical air handling system, you can have a carbon filter as part of the air handling unit. And that's a very good way of taking ozone out of the air that might be generated by the UVC. In the United States, it's very common for us to recirculate air in commercial buildings. And so if you've got a charcoal filter in the air handling system, that recirculation is going to be constantly taking ozone out as the air goes through the filters. If you don't have a mechanical ventilation system, if you're talking about an old classroom or a home that doesn't have central AC, standalone air cleaners can be fitted with carbon filters. You want to use enough carbon. You want to make sure that standalone air cleaner is set up, designed to remove ozone. But that can be done, and that can really reduce the chemistry. So there are mitigation approaches. A closing thought. I began by talking about the epidemiology and the fact that the associations between ozone and morbidity and mortality tend to be based on ozone measured outdoors, but we recognize that a large fraction of our exposure to ozone itself and the products occurs indoors. This indoor exposure to ozone oxidation products likely contributes to the adverse health effects that have been observed. But the question is how much? And this remains an unanswered question. I wanted you to appreciate that as well. I want to thank two colleagues who've played a role in the material I presented over the last 20 minutes or so. Bill Nazaroff from UC Berkeley, now emeritus, Jim Jung from Duke University. I thank you for your attention. I've tried to leave time for questions, and I'll be happy to try and answer questions you might have.